All right, I want to take a look at some logarithms just for review. So I'm going to try and do this all in one shot. So go ahead and just follow along with me right here. So first off, for logarithms, some essential understandings. The definition of a logarithm, you need to understand that every single logarithmic equation is equivalent to an exponential equation. So if I have b to the u equals v for some base and some constants u and v, then that will always be equivalent to the log base b of v equals u. You need to understand that when you take this, the base stays the same. Notice this is a subscript, it's down low. But what is going inside the logarithm is v, the output. What the logarithm equals is the exponent. All right, so we need to have this basic relationship down. And this is the abstract version. If it helps you, think of it in more concrete terms. An example might be like 2 to the third equals 8. That is equivalent to the log base 2 of 8 equals 3, because the third power of 2 is what gives me 8. That's what the logarithm is asking. Some other things we need to know. Log properties, because remember we're going to have to use these as well. The log base 6 of 3x. So if I have multiplication inside, because that is 3 times x, outside the logarithm I should have a sum. So I should have the log base 6 of 3 plus the log base 6 of x. If I have a quotient inside my logarithm, so here I have the natural log of a over b, which I know that's a log of base e. Division inside means outside I have subtraction. So the natural log of a minus the natural log of b. And my final log property that we used, if I have an exponent inside, so here I have a log base, common log, which is base 10. So the log of z to the fifth, that exponent inside the logarithm gets multiplied in front of the logarithm. So I get 5 times the log of z. Now, in addition to all of these properties, another property that you need to be familiar with, even though most of you don't need to use it with the newer graphing calculator, is the change of base formula. And that is, if I want to evaluate a logarithm for some particular base other than e or 10, which natural log and common log are on any standard scientific calculator, if I want to evaluate a logarithm for some other base, I can do it in terms of common log, or for that matter, natural log. But the log base b of u is the log of u divided by the log of b. And you can always think of this in plain terms. This is the log of whatever is inside the logarithm divided by the log of the base of the logarithm you started with. So for example, when I come down here, if I wanted to do the log base 6 of 100, on a newer graphing calculator you can pick the base, but I could also do this using the change of base formula. So if I want to evaluate these things, I'm just going to go right ahead and do that. Some of these you can just do if you understand the way exponents work and what logarithms represent. The log base 3 of 81, you can confirm with a calculator. Again, I'll show you right here. If I go to math and down to a, there is log base, and this will allow me to pick the base for my logarithm. And what I can do here is pick base 3 and 81, and if I hit enter, it'll give me the answer. What is the answer? Well, this is asking me, move this off to the side, what power of 3 equals 81? And the answer is, of course, 4. My calculator agrees. So I can do that for several of these. If I have here the log base 1/2 of 16, that one's a little bit more challenging. But again, what power of 1/2 gives me 16? Well, I need to understand, of course, that 1/2 is the reciprocal of 2. So if I took its reciprocal and then raised it to the fourth, 16 is 2 to the fourth. So this is actually 1/2 to the negative fourth is what would give me 16. So this is negative 4. And again, you can check with a calculator and it will confirm that. For C, the log of 100,000. So again, we understand the base is 10. Common log is base 10. What power of 10 gives me 100,000? Well, I know as I take higher powers of 10, I get a larger number of zeros. So if I have 5 zeros, this must be 10 to the fifth. And again, common log right here on my calculator, I can just, let me move that down so you can see my screen. I hit log, and then I do 100,000, and I can close it, and it's 5. Now those are all nice numbers. You could figure these out, and I did figure them out without using a calculator. What about for things that are not as nice? Well, if I look down at these examples right here, the natural log of 50, the log base 6 of 100, the log base 9 of 5. So, the natural log of 50, again, just go to your calculator. Natural log is right there below log. Hit natural log, and then I want the natural log of 50. And close this, and that is approximately 3.912. All right. When I want to do these other ones, again, you can go to the log base. I'm going to use the change of base formula just to get practice with it. So here I would take the log of whatever is inside, 100, and divide it by the log of the base that I am using, which is 6. What does that give me? Approximately 2.570. And again, I'll do the next one right here. The log base 9 of 5, which again, if I think in terms of the change of base formula, is the log of 5 divided by the log of 9. Now mind you, 5 is less than 9 to the first, so I know that this should be somewhere between 0 and 1. So if I do this, the log of 5 divided by the log of 9 is 0.732 approximately. All right. So that's pretty simple stuff. Like I said, you can use the calculator for all of these. Hopefully we understand how to do these ones that are doable without a calculator. Let's take a look at some other examples. Here, I want to find the 0 of each log function. So the 0 of a function means where y equals 0. And of course, when you're dealing with functions, you have to remember that f of x, g of x, h of x, whatever it happens to be, those are all equivalent to y. So when I want the 0 of this function, 0 is equal to the log base 9 of 7x plus 15. In order to solve a log equation, what you want to do is have the logarithm isolated, which we do, and then I want to rewrite this in an exponential form. So the base I should use is 9. The logarithm equals the exponent. So that is my exponent, 0. So 9 to the 0 yields 7x plus 15, whatever x is. Well, 9 to the 0 is 1. And then you can solve this equation, get negative 14 equals 7x. Thus, x is negative 2. All right? And I'll go ahead and do the next example, too. So, same idea. It's going to be a little bit different because of this negative 2 right here. So what I want to do, again, I want to find the 0 of this function. So y, which is f of x, equals 0. And I take the log of 12x plus 12 minus 2. So I have to isolate the logarithm. So I'm going to add 2 to both sides. Here, let me underline this whole thing. I can't, of course, isolate log itself. It is the log of 12x plus 12. It's going to stay the log of 12x plus 12. Add 2 to both sides, and the log of 12x plus 12 is equal to 2. Again, if you rewrite in exponential form, the base of a common log, we understand, is 10. So 10 squared is equal to 12x plus 12. I'm going to come over here because I'm running out of room. 10 squared is 100. 100 equals 12x plus 12. I subtract 12. 100 minus 12 is, of course, 88. And if you divide by 12, you can take out a common factor of 4. And your answer is 22/3. So that's how you find the 0. I'm going to go ahead and turn this over and look at some more solving related to logarithms. And also using the properties. So here I want to expand each logarithm. So again, the idea is look at what's going on inside, 6w to the 4th over v cubed. So I know I had those 3 rules, multiplication inside, division inside, and exponents inside all can be brought out of the logarithm in some fashion. So I understand up here this is 6 times w to the 4th, and it's divided by v cubed. So I'm going to do this. This is an arrow. I'm going to do this as quickly as I possibly can and split this all up. Upstairs I have the product, log base 5 of 6 times w to the 4th. multiplication inside becomes addition outside. So the log base 5 of w to the 4th divided by v cubed. So then that becomes subtraction outside. The log base 5 of v cubed. All right. Now there's a little bit more simplification I can do here. These exponents inside the logarithm can be multiplied out front. I would also look here and see if I can simplify this at all. The log base 5 of 6 is just some funky number, so I can't do anything with that. But here I can rewrite this and have 4 times the log base 5 of w minus 3 times the log base 5 of v. All right, and that's as expanded as I can possibly make this. Notice that inside each logarithm, nothing is multiplied. I guess in theory I could split 6 into 2 and 3, but let's just pretend I didn't say that. Let's go ahead and do the next one. I have here 3 over xy to the 5th. So understand, that means 3 is being divided by both of these factors. So it's 3 divided by x times y to the 5th, but since these are both divisors, sorry, I need to flatten out my paper. Since those are both divisors, that means I will need 2 subtractions when I split this up. So I will have the log of 3 minus the log of x minus the log of y to the 5th. That exponent can be brought in front, and I will have the log of 3 minus the log of x minus 5 log y. And that's it. All right. Let's move right along. Let's get to the solving, because this is a tricky point for some different reasons. Here, I want to solve these equations. I want to show my exact answers and round to the nearest hundredth are my instructions. So understand, those sound conflicting. The idea is you're going to show me all the work and then approximate only in the final step. So here, you want to add 10 to both sides. So 6 to the x plus 4 is equal to 55. All right. And then I want to rewrite this in logarithmic form. So I will say the log base 6 of 55 is equal to the exponent. The exponent was x plus 4. To solve for x, I will now subtract 4 from both sides. So you can write this a couple ways. Perhaps the best way is to write negative 4 plus the log base 6 of 55. You could also write log base 6 of 55 minus 4, but understand 55 is inside this logarithm. So it better stay 55. If it changes from 55, you have a problem. You're not doing it correctly. So that is my exact answer. If I want to approximate this, again, I will go to my calculator. And I'm going to show you, if I do this, let me just clear my screen. Negative 4 plus, I'm going to use the log base feature. Log base 6 of 55. And if I do this, I get negative 1.76 to the nearest hundredth. Now, we talked a few minutes ago about change of base formula. Some people don't have this log base feature available in their calculators, so I'll show you how you do that. Well, same basic principle, negative 4 plus the log base 6 of 55. Using change of base formula, I know I take the log of whatever's inside, close that, and divide by the log of the base. And you'll see that I will get exactly the same answer, negative 1.76. So I'm going to write that x is approximately negative 1.76. The instructions ask me to give both answers, so I do. Here, B. I have 1/5 e to the 3x minus 6 plus 4 equals 7. So the idea is I need to isolate the exponential. I'm solving for x. X is in the exponent of e. So I need to isolate this first, which happens to have a 1/5 attached to it. So in order, I need to subtract 4, and then I will deal with the 1/5 to isolate that exponential. So 1/5 e to the 3x minus 6. I subtract 4 from both sides and get 3. I need to get rid of the 1/5 now. So what I want to do is multiply both sides by 5. 5 times 1/5 is 1. So I'm left with e to the 3x minus 6. 3 times 5 is 15. All right, so now I want to rewrite this in logarithmic form. If I rewrite this in logarithmic form, e is a natural log is what I want to use. So I will take the natural log of 15, and that will give me the exponent, 3x minus 6. If I want to solve this, I will have to, in order, add 6 and divide by 3. So again, you can write this a couple of ways. 6 plus the natural log of 15 equals 3x. For the exact answer, you could show me this, 6 plus the natural log of 15 all divided by 3. You could alternatively write 2 plus 1/3 the natural log of 15. That's also equivalent. And then I need to actually approximate this. But your answer should be one of these two. Or again, you could put the 6, you could write natural log of 15 plus 6. All right, so let's approximate this. So 6 plus the natural log of 15 divided by 3. Be careful how you enter this into your calculator. You could also kind of just think about how you actually did this problem, which is you had the natural log of 15. I added 6, and then I divided that result by 3. I want to see this exact work, but if you're putting it into your calculator, this is just as efficient, quite honestly, and will give you the same answer as if I did 6 plus the natural log of 15. Notice I've taken this whole numerator and put it in parentheses and divide by 3. And I get 2.90 to the nearest hundredth. So those are my answers. Be careful how you enter these things into a calculator. As I said, if you're doing something like this where it's in a fraction format, you need to understand that the numerator has invisible or understood parentheses around it. So when you're entering it into the calculator at once, you need to do it like that. Or you could do it in the multiple steps as I showed a couple minutes ago. All right. Let's try a couple others. This was using logs to solve exponentials. How do I solve a log equation? Well, we talked about two types. If we can rewrite an equation as a log equals a log, then the insides must be equal. But here, I just want to look at what about if I can get the log of some base of some argument equals a number. So here, 2 log x minus 5 is equal to 1. So what I can do is add 5 to both sides. I'm trying to isolate the logarithm. So to isolate the logarithm, I need to be careful how I write this, because x is not the base, so it should be on the same line as the logarithm. Divide by 2. So the log of x is equal to 3. All right. Now, in order to solve for x, I need to get it out of the logarithm, which means I need to rewrite an exponential form. So the base is 10. 10 to the exponent, again, the exponent is 3. 10 to the third equals x. Well, 10 to the third is 1,000. And that's it. Since my argument inside the logarithm was very simple, I don't have any real math to do. It's just 1,000. Once I have 10 to the third, I'm done. All right, one last example right here. B. The log base 7 of 4x minus 5 minus 8 is equal to negative 6. All right, so again, I want to isolate the logarithm. So I will add 8. Log base 7 of 4x minus 5 is equal to 2. And then we want to rewrite in exponential form. My base is 7. The logarithm equals an exponent, so 7 squared gives me 4x minus 5. 7 squared is, of course, 49. If I add 5, I get 54. If I divide by 4, that makes x 27 halves. And that's it. Hopefully this has been helpful. Remember to study. Remember there are also, this is not necessarily an inclusive review. You definitely want to also look at exponential regression was one of the things that was not covered in this review packet, but it is in your notes and it is also on your task review. So you should consider those problems as well. But hopefully this has been helpful with working with logarithms.